So since we're going to be working with exponential functions and eventually graphing them, let's define what an exponential function is. It says an exponential function is the function in the form of f of x equals c to the bx power, where b is a positive real number. B must be greater than 0 but not equal to 1, and I'll show you why it can't equal 1 in a future video. And c cannot equal 0 but is a real number. I have underlined that the domain of the function is the set of all real numbers, so any and every exponential has a domain of negative infinity to infinity. The base b is the growth factor, and because f of 0 equals c to b times 0, and we just set up here, anything to the 0 power is 1, then that means it equals c. So what does that mean? C is called the initial value. So C is what's in front of that exponential portion. That exponential portion of this is b to the x power. And what makes an exponential function, how you can look at it and tell, is because your variable will always be in that exponent position. So a lot of times we're going to have it to the t power, but that variable can be any variable it wants to be. And so an exponential function, you can look at because that variable is in that exponent position. So in example 1, it says in a protected environment, the population P of a certain endangered species over time. Let me start over. I'm so sorry, guys. I'm struggling today. Okay. In a protected environment, population P of a certain endangered species recovers over time t in years, according to the model P of t. So what is the size of the initial population? So that keyword initial population is what's in front of. So because this is 30 times your exponent, we are talking about 30. 30 was my initial size of the population, the initial population. Yeah, the size of the initial population of species. I'm sorry, I'm sure this is so hard to listen to me just repeating words over and over, but the size was 30. Okay. Herbie, according to this model, what will the population of the species be in 5 years? So this 5 is talking about my t. So I'm going to take this, I'm going to replace this t with what they give me. So P of 5 equals 30 times 1.149 to the 5th power. So let's find what this is about. All right. So 30 times 1.149 to the 5th. And we get about 60. So because we're talking about some kind of animal, I want to round to the nearest whole number. I can't have 0.10 of an animal, you know, a tenth of an animal walking around my zoo or whatever. So we're going to round to the nearest whole number. So what will the population be? It'll be 60 species. Okay, what will it be in 10 years? So this is my new t. So now let's find P of 10. So 30 times 1.149 to the 10th power. So all we need to do is arrow up and highlight and change that 5 to a 10. So if again, I'm rounding to the nearest whole number, whole animal, 120. Okay, now when I'm teaching this on campus, I always ask, what do you think it will be then in 15 years when we replace that T with 15? Okay, pause the video if you want more time to think about that. So let's arrow up and highlight and change that to 15. Usually I get the guess of 180 and it is 240, or if I round properly, 241. So this is not linear, right? Where it's increasing at a constant rate of change. 60 to 120 is 60, another 60 would be 180, but we got to take this 30 into account too. So what's happening from 30 to 60, 60 to 120, 120 to roughly 240, but 241. What's happening to the population every 5 years? It's doubling. And so we will find that things are going to start increasing really, really rapidly. So they'll either double, you'll get them where they are tripling or quadrupling. And so these are not going to have constant rates of change anymore. These are going to start off kind of slow and then just fly off the charts on that Y value and increase really quickly, or vice versa. They're going to increase really, really, or decrease really, really quickly, and then kind of start leveling out.